So what guys is finding eigenvalues. All right, so we're finding eigenvalues in the warm-up. So we're going to start by using our equation. A minus lambda I, we're finding the determinant of that and finding out when that determinant is equal to 0. So that determinant is minus 1 minus lambda, 2, 4, and 3 minus lambda. Essentially subtracting lambda on the diagonals. So now we do the determinant calculation. I'm going to get negative 1 minus lambda times 3 minus lambda minus, that should be a negative 4 down here, minus a negative 8, so that's positive 8. We'll multiply that stuff out. We'll get negative 3 plus lambda minus 3 lambda plus lambda squared. This again plus 8. And I'll reorganize here. Lambda squared minus 2 lambda plus 5. And the question is, when's that equal to 0? Now we can look at that for a while and see if we can try to find a factorization. I can't see anything that jumps to mind. I don't want to spend too much time on it. Of course, this is where you might want to check it with your calculator to see if there is a nice factorization or not. But if not, you can always use your quadratic formula. Say, when is this thing equal to 0? When lambda is equal to negative b plus or minus the square root of b squared minus 4ac all over 2 times a, where a, b, and c are the coefficients of that polynomial. We'll simplify this thing a little bit. Under the radical, I have the square root of negative 16. So the square root of negative 16 is going to be plus or minus 4 times I, imaginary number, all over 2. It simplifies to 1 plus or minus 2i. All right, so those are the eigenvalues, and there's 2 of them, 1 plus 2i, 1 minus 2i. So I have my 2 eigenvalues that I expected from this 2x2 system. I have both roots here. Now, are there any questions about that process?
Yes.
All right, which spot here?
Okay, under the radical.
Under the radical, absolutely. All right, people have a wide variety of experience with complex numbers. Some people will have never seen it coming as a course. Some people will have seen it quite a bit. So by definition, I is equal to the square root of negative 1. That's the definition of the imaginary number. Right, so how do we take square roots of things? We don't really have a process for that. We take 2 squared, we get to 4. What number squared gives us a negative value? Well, we don't have any numbers to do that, so they came up with the imaginary numbers. So by definition, you say that I squared is equal to negative 1. So when we look at what's under the radical here, we have the square root of negative 16. So we can kind of write that as the square root of maybe negative 1 times 16. And when we have a product under the radical, we can really look at it as the square root of negative 1 times the square root of 16. So then, almost by definition, we have the square root of negative 1 is I, and the square root of 16 is 4. Okay. We have to be a little bit careful with these i's. Now, we have the definition, but how it's defined means some things go a little weird. Right? If you have an I in the denominator, you have to be careful with how you put it into the numerator. Okay, does that answer the question?
Absolutely.
Okay. So after we get to here, we're just simplifying the fraction out to get the 1 plus or minus 2i. Okay. So those are our eigenvalues.
That helps a lot.
All right, our plan of attack for today is to work with complex eigenvalues and eigenvectors. We did the eigenvalues. Now we have to see if we can get eigenvectors from there. After that, the question will be, can we diagonalize A with these complex eigenvalues? That was a priority. So now can we do it when we have complex values? And then the last one is, can we simplify the transformation using real numbers? So we somehow translate the information we get from these complex systems to maybe real numbers where they actually mean more to us, where we kind of see what they do. Those are the 3 goals for today. All right, so from the warm-up, this is what we were left with. We have our matrix. We found our eigenvalues. And now it's time to find some eigenvectors. Okay, so we're going to go through this one together because there is a little bit of tricky algebra in here and a couple of realizations that will help simplify our work so we don't have to do too much by brute force. Okay, so we're going to start off by choosing an eigenvalue. We're going to start off with lambda equals 1 minus 2i. Now I'm going to start off with a negative, mostly by convention. That's just how we tend to do it. Also because it actually helps as we go along. If we think about our a minus lambda I piece, we're subtracting lambda. Well, if I subtract lambda, it'll be negative this thing, and then minus a negative turns into a positive. So I'll be working with positive values, which is always kind of preferable. That's maybe a practical reason why we choose this. But as we make this choice, later on we're going to use formulas to do stuff. In differential equations, you have to work with eigenvectors to solve differential equations. And so they'll say, when the eigenvalues and eigenvectors are this, here's a formula for your solution. Those formulas tend to be based on lambda equals 1 minus something, a minus bi. Right? And so it's not really a matter which one you choose, but if you're going to use a formula that's based on 1, you have to make sure that it's really based on 1. Right? So you could do it the other way around, you have to change some signs later. But you just have to be aware that there is some thought in that choice. Okay, so we're going to start with this one, and we're really going to plug it in. We're going to plug it into a minus lambda I, so we're subtracting minus 1 minus my eigenvalue here. I'm going to write this all out so we just make sure that we don't drop any signs along the way. That is, without a doubt, the common mistake. Okay.
Is that 1 minus lambda I?
Yep. So we have a minus lambda identity. X equals 0. That's the system we're trying to solve now. So that matrix will look like negative 1 minus lambda, 2, negative 4, and 3 minus lambda. And so when we put in our values for lambda, I'm just chunking them right in there with parentheses, saying this is the lambda piece that I'm plugging in. And I'm using those parentheses, so I want to make sure I don't forget to distribute that negative sign. So it's a homogeneous system, so I really have to write this matrix and just row reduce it. That's kind of what I'm going to do. First, I'm just going to distribute the negative sign and simplify a little bit. On the first term here, I'll have negative 2 plus 2i, 2. Then I'll have negative 4 and 3. 3 minus 1 is 2, plus 2i. Once again, the most common mistake is not to distribute your negative sign. And now what would I do? To finish row reducing, right? That would be a giant pain. I mean, I could certainly go through the steps. I want to turn this into a 1. Before I can turn it into 1, I want to turn it into a real number. So to turn a complex number into a real number, I would multiply by its conjugate. And what's a conjugate? Well, if I have some complex number that looks like a plus b times I, right, like 2 plus 3i or 4 plus 6i, the conjugate is just a minus bi. You just change that sign in the middle. And if you multiply those two things out, if you multiply these two things, you get a squared, the middle terms have disappeared, and you end up with minus bi squared. And when you square this thing, the I will disappear. Right? So you can turn a complex number into a real number by multiplying by a conjugate. Now we could go through that process. We could multiply by the first row by the conjugate, so we can multiply rows by numbers. Now we turn this into a real number, divide by that number to turn it to 1. We can use that to eliminate this. We go through all that work, but we don't have to. Right? We don't have to because I know how this is going to simplify. I know that this row is just a multiple of this row. It's hard for me to see right now because I have these complex values. But there is some magic number, complex or real, I can take times this row to get me exactly this row. How do I know that? How do I know that these rows are multiples without actually doing the row reduction?
What's the even numbers?
What's that? They are multiples. I'm not sure of what. It's going to be like 1 plus I or 1 minus I or something weird there. It's going to be a little more complicated. I don't have to find it. I know they're multiples. Because if they weren't multiples, then when I row reduce this thing, right, if they weren't multiples, so if I couldn't say 2 times this, eliminate this whole row, well then I would eliminate this first term and there would be some number here. In other words, if they weren't multiples, eventually they would row reduce to something that looks like this. If they weren't multiples. That's bad. That means there's only one solution. If there's only one solution to this homogeneous system, what is that solution? Trivial solution, 0, but 0 isn't an eigenvector. All right, so I'm finding these eigenvectors. I know that 0 isn't an eigenvector. I know I'm going to have more than one solution. That's what I'm trying to find here. So I know these things have to be multiples. Okay, we've kind of set that up from the start. We're finding the vectors specifically that give us these non-trivial solutions here. So I know they are multiples. And once again, if you don't believe me, you're more welcome to check. Right, it's not actually that bad. You multiply by the conjugate, you play around a little bit, and you will see that they're multiples. But because I know that, because I don't have to do that work, I know it's going to reduce to some row with a 0, 0. I know they're just multiples. All I really have to do is pick a row and work with it now. Okay? So I'm just going to grab the first row here. Say that first row tells me that x1 times negative 2 plus 2i. I'm going to grab this one. Yeah. Plus 2 times x2 equals 0. And I'm just going to use this one row to form my solution. I certainly could have picked the second row. It doesn't really matter which row I pick. Now once I choose a row, all I'm going to do is solve it for one of the variables. It doesn't really matter which one. Well, I shouldn't say that. It doesn't really matter which one, but boy, I want to do the easy way, right? I don't really want to solve x1 because when I start dividing by these complex numbers, things get a little weird. So try to avoid that. I'm just going to solve it for x2. I'm going to subtract x2 over here. Look at x1 times negative 2 plus 2i equals a negative 2x2. I'll divide by a negative 2. Look at x2 over here. And on this side I will get 1 minus I. Any questions so far? Okay, now I'm going to form my solution. When I look at that last equation here, it tells me that x1 is my free variable. I expected to get a free variable. I had to get a free variable. That's another reason you could say that I knew the rows were multiples. Now when I write it like this, I'm treating x1 like it's the free variable. You choose x1, I would know exactly what x2 is. So x1 is like my free variable here. So I'm going to write out my solution now. My solution, just like always, is an x1 value and an x2 value that make this a true statement. I just said that x1 is going to be my free variable. And then x2, well, I've already solved for x2. x2 would be x1 times 1 minus I. I'll factor out my parameter, and I'll get my eigenvector of 1 and 1 minus I. So that's my eigenvector. The most important step here was saving ourselves some work, not wasting our time with the row reduction. Understanding that as soon as we plug this in, these rows are multiple. I can just use one of them. I just pick a row and I use that equation to generate my solution. Any questions so far? That was the bad news, right? It's a little more complicated. Not too bad, but it's a little more complicated. Some uglier algebra. Now for the good news. Look at our lambdas. Look at our eigenvalues. We said it was 1 plus or minus 2i. Those are conjugates of each other. Right? I used 1 minus 2i, it's my first eigenvalue, to generate an eigenvector that was 1 minus I. Turns out when I use lambda 2, which is just the conjugate of lambda 1, the eigenvector that I'm going to generate is just going to be the conjugate of the first eigenvector. Now, how do I take the conjugate of that thing? Well, I know how to do the bottom one, right? That's 1 plus I. But what's the conjugate of 1? Turns out it's just 1. All right, so here's our complex number, a plus bi. Right, the complex numbers are really a set of numbers. In fact, they're a really big set of numbers. They're bigger than a set of real numbers. In fact, every real number is a complex number. Right? It's just 2. 2 is just 2 plus 0i. Right? So the complex numbers actually includes all of the real numbers. It's just a special case of complex numbers. And so if I have a complex number that is 2 plus 0i, and I look at its conjugate, that would be 2 minus 0i, which once again is still just 2. So the conjugate of a real number is just that real number. So the conjugate of 1 is just 1. So the good news is we only have to do it once. We only have to use one eigenvalue and we get both eigenvectors from that. All right, now just like I have complex numbers that look like a plus bi, I kind of want to write my complex eigenvectors like that too. So that's what I'm going to do. I'm going to have complex vectors, and I'm going to write that as a vector plus a vector times I. So for instance, my first eigenvector, I could rewrite that like this. I could gather up the real parts. And this is associated with the minus eigenvalue here. So I'm going to say minus I times, and I'll gather up the imaginary parts. That's kind of like how we formed our parametric solutions. And over here, this other one would be 1, 1 plus I times 0, 1. So it's just another way to write out those eigenvectors. And that's the terminology we use as well. When we talk about complex numbers, like 1 minus 2i, we say that 1 is the real part of the complex number, and we say that 2 is the imaginary part of the real number. Now when I say that 2 is the imaginary part, that imaginary part is a real number. Right, this is the coefficient to the I term. The I is the imaginary number, but the coefficient to the I we call the imaginary part. So we have the real part and the imaginary part. Okay, same thing here. I'm going to have a real part and an imaginary part. Sometimes we'll label those as real and imaginary. All right, questions so far? Essentially, we proceed like normal. We find the eigenvalues. They're complex. We plug them in the same way we do regular eigenvalues. And then the trick is we just pick a row and form our solution from that one row. And then the second eigenvector is just the conjugate of the first eigenvector. All right, let's see if we got it. Eigenvalues, eigenvectors for this one. See how far you can get. If you get stuck, make sure you ask. Now I chose the first row last time. Totally random. Could have chosen the second. The eigenvectors will look very different. Doesn't mean they're wrong. It means they're different. Now, regular problem, you found an eigenvector of 1, 2, and said it was 2, 4. We would kind of know that we're both right. So they're just multiples. It's harder to see if they're multiples when you have complex values in it. They still could be multiples.
16 minus 2. That's why I lost. Get lost right
You can take right at this point. You can take this and put it in a calculator.
here. Okay.
So there's no way to have that as an option.
P9?
Yeah, so give them magnitudes.
Yeah.
Take it out, change it. Yes, 0. I don't know if that is something. Squared. Minus 4 times. That's fine. And I have to tell what my variable is. So my variable is 5x. So we need more rows. So for instance, this one would be 2. That factor, because that is those times.
Yes.
Together. So we're not giving them imaginary rows. Complex zeros. Totally with mine out. Yeah, check. I'm making stuff up on mine here. This should be 4. Now I changed it. This should be the square root of negative 4. Should be 4 plus or minus 2I over 2. 2 plus or minus 5. So this one is quadratic formula.
Yeah.
You use that or you
Okay, so doing this by here, still not right 16 minus 2.
Okay. It's a big ugly formula. It's just a formula that I have memorized. It's negative b. So if you have this thing, ax squared plus bx plus c equals 0. That's 0 when x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. It's called the quadratic formula.
Okay.
It's giant. So this might be a common question here. How many people are just in love with the quadratic formula? Anybody have tattoos? Lower back or something? Quadratic formula. If you don't have this memorized, which is totally understandable, right? If you don't use it all the time, you're not going to have it memorized. You're more than welcome to take this thing and put it in your calculator. Just make sure you know how to do it. Okay, so there's going to be 2 kinds of zeros, one for real solution and one for complex. You have to make sure that you can find both those on your calculator. Because if you can't use your calculator to do this, then you have to have this memorized and go through it to find the roots. Because you're expected to be able to find roots. Okay? So I know this is one thing that they kill you on in high school and they make you memorize it, and then a year later you forget it. You might never use it again. But you either got to be able to do it in your calculator or have this memorized, either way.
Okay, so what do we So I'm having a problem labeling the A's, the B's, and the C's in our current problem.
So for ours, we have the coefficient of the square term is a. So a is just 1.
Right.
This will 1. And then b will be negative 4.
Okay. So that's the 4 squared, that's 16.
Yeah.
Well, that's just like notation.
Yeah. And I have minus 4 AC. So c is 5.
Okay.
Okay.
So that's 4 times 5, that gives 20. Okay. I got it.
All right, yep, so I would just write that one down as the quadratic formula, and
A is 1 and C is 2.
you're welcome to practice that one. It's kind of up to you. It's not in the course so much. Okay, so I've gone through and found the eigenvalues, and now we're going to go find the eigenvectors. So I'm going to take my first eigenvalue, when lambda equals 2 minus I, and I'm going to plug that in and see what we get here. All right, so I'm going to plug that into my homogeneous system. I'm going to get 1 minus lambda, so that's going to give me negative 1 plus I. Make sure we're careful with the signs. 1 minus 2 and then positive I. Then I have a negative 2, I have a 1, and I have 3 minus lambda, so that will give me 3 minus 2, which is 1, and then plus I again. Make sure I'm changing my signs. So once I put that in there, once again, it's just a matter of choosing rows. I could choose either row. I could work with the equation that says x1 times negative 1 plus I minus 2x2 equals 0, or I could deal with the row that says x1 plus 1 plus I times x2 equals 0. Choose either one is fine. I'm going to choose a second row this time because it's almost solved for x1. I don't have to divide by anything. It's just a little bit easier. So that's the row that I'm going to choose to work with. So if I choose this row, I'm going to solve it for x1. It's just, what do we have here? Negative 1 minus I times x2. So I have that. So now for my solution, x2 is my free variable in this time, so x2 is just x2. And then what's x1? It's negative 1 minus I times x2. So it looks like my eigenvector will be negative 1 minus I and 1. So I have lambda equals 2 minus I. That gives me the eigenvector, negative 1 minus I and 1. And then I know right away that my second eigenvalue, 2 plus I, should give me an eigenvector that looks like negative 1 plus I and 1, the conjugates. All right, any questions about those? A lot of repetition, a lot of practice. Once again, the tricky thing is that it's harder to check these answers because the eigenvectors can look very different. So to kind of give us a sample of that, let's take a look at, this was from our warm-up. So I'm going to scroll back up to our warm-up real quick just to see the solutions. There are solutions from the warm-up. And in Mathematica, we just define the matrix, run eigensystem. It will deal with the complex values no problem. Sure enough, we got 1 plus or minus 2i. They will order these, so 1 minus 2i should be associated with this eigenvector right here. And that certainly looks a lot different than my eigenvector. Right? I had 1 over 1 minus I, and they have some fractions of the I in the top. They must use the other equation. Right, so there is some factor that would go back and forth. Let's see if we can find it maybe. How about I type in a factor and try to see what I get. I'm going to multiply that eigenvector, that second eigenvector. I want a conjugate, so I'm going to say 1 minus I. Now when you use I in Mathematica, you can't just type I. It has to be escape, I, escape, to get the actual imaginary number. If I times that, what do I get here? 1 and 1 minus I, there it is. So they were just a factor different, even though they looked really ugly, because the factor was 1 minus I. So 1 minus 2i is the eigenvalue, and this is the eigenvector that I got. So we can check them with calculators or with Mathematica, but you have to be a little more careful. All right, so now we're going to go on to diagonalization. Can we diagonalize? Now we know how to deal with the complex eigenvalues and find the associated eigenvectors. The question is, what do we do with them? One of the big values before was diagonalizing. That's valuable for a lot of reasons. One, it kind of shows us what the transformation is doing. But another reason that we haven't talked about too much is because we can use it for differential equations to decouple a system. So in differential equations, if you're dealing with more than one variable, you might have derivatives like this that are functions of more than one variable, x1 and x2. These are kind of intertwined systems that are dynamic. But if we can decouple the system, so we might have dx2 dt equals 2x1 plus 3x2. Both of these derivatives depend on x1 and x2. And so if we wrote this out as a system, we can actually make it look like a matrix equation. And it turns out that this coefficient, 1, 1, 2, and 3, would be a matrix that's involved in this differential equation system. The process of diagonalizing, decoupling, means this right-hand side turns into just x1 and just x2, which makes these differential equations much easier to solve. So one reason we like to diagonalize is because it helps us in differential equations to take systems and simplify them, to make them easier to solve. It's called decoupling the system. How many people are going on to differential equations next? Most usually. Okay. Something to look forward to. Yay. Now, we could actually just diagonalize like normal. Right? We could just say, these are my eigenvectors. I'm going to throw them in as my columns for P. I'm going to diagonalize just like I did before. Is that going to work? Let's see. Here's A. Here is my eigenvalues. I can delete this little cell now here. And then I have taken the eigenvectors and I've formed a matrix P. And so I'm having P times that diagonal matrix times the inverse of P. And sure enough, I get back to the matrix I wanted. So in theory, you can just diagonalize like you always did. But that's not very useful to us. Because what that diagonalization tells us is what this transformation kind of looks like at its core. When we diagonalize, if this was 2 and 3, it says that at its core, that matrix is doing a stretch and a stretch. Well, I don't know what it is to stretch by 1 minus 2i. I don't really know what that means physically. So I can't really see what this thing is doing. That's really why I want to diagonalize in the first place. So first, let's take an example of what a regular matrix diagonalization tells us. All right, so here's a matrix A. I have pre-diagonalized it. We found our P, our D, and our P inverse. We talked about this a little bit before of what each of these things is doing. If I take A and take it and apply it to some vector or some set of vectors, it's the same thing as then applying all these matrices to that vector, and they each have a specific job. This first one is essentially a change of basis. It's going from the standard basis to the eigenbasis. We're using a new basis. And then D essentially applies our transformation. It's a lot easier to apply this transformation than it is this transformation. Now this one's actually a pretty simple example. I can kind of see what this one is actually doing. But it's very easy to see what this one is doing, regardless of how complicated A is. This says we're stretching, we're doubling, we're stretching in the x direction, and we're keeping the y direction the same. It's almost like another change of basis, going from 1, 0, 0, 1 to 2, 0, 0, 1. So all we're doing is stretching in the x direction. I can see that very easily by looking at that matrix A. And then the final matrix is just changing our basis back. Changes the basis back. So what might this kind of look like here? Let's take a look at an image and see what all these steps do. So this code will be a little bit bulky. Don't worry about it. Doesn't do all. You don't need to know what all the individual pieces do. First part is just capturing an image and then organizing the image so we can use it. And now I have my matrix A the same way I just showed here. I'm going to find the eigenvalues, eigenvectors, and I'm just going to show you what all those matrices look like, the ones we just kind of wrote down, right? These are these three matrices. We have P, D, and P inverse. So we kind of see what they do. And so now we have our picture. This is our picture right here. On my side, because that's how the data is organized, I would have to adjust if I wanted, but this is just how it comes on the side. And so if I multiply by my matrix A, this is what it does to the image. And once again, we could kind of expect that just by that matrix. It's a shearing matrix if we looked at it. But it's a little more complicated than just a regular transformation. So what this thing is really doing is says, okay, first, let's change our basis. And the basis we're going to is P inverse. So P inverse is this one, right here. So instead of 1, 0, and 0, 1, we'll start with this one. Instead of a nice 1, 0, 0, 1, we're going to use 1, 0, 1, 1. So it's going to slant this image down. That's the first thing. We're going to change our basis to use the eigenbasis. Okay, and it kind of does what we expect. We can see what that change of basis does. The next matrix we'd apply to it would be D. Well, what's D going to do? Here is D. I multiply by D. What is D going to do to it? See a couple hand motions here. We're just going to stretch it in the x direction. Instead of that vector 1, 0, it's going to turn it into 2, 0. So when we apply D, it does a very predictable thing. It just stretches everything in the x direction. We can see that clearly from the nature of the matrix. And the last thing is just going to readjust for the coordinates. So the first coordinate system kind of squishes down like this. This should be undoing this and bringing this back a little bit. And that's how we got to where we got to. Okay? So that's really the process of applying that diagonalization. It breaks the transformation down into these little bitty steps. Now, that might not be too useful for this matrix because it was relatively simple from the beginning. But a more complicated matrix, it's hard to see exactly what it's doing. But if we break it down into these components, it's going to be more natural. Okay. So the reason we do that is because I can look at D and I can see exactly what it does. The problem up here is that I can't see exactly what this does. I have no idea what that thing is doing. So it would be better to characterize our transformation using only real values instead of these complex values. I really can't tell what they're doing. All right, so this is what I got so far. This is what we did. We found the eigenvalues. We found the eigenvectors. I'm going to start with the eigenvectors. I don't want to use complex ones. I want to use some real ones. Now remember, these eigenvectors are not the only eigenvectors. I can use any eigenvectors I want here. I grab one eigenvector from each eigenvalue because I know they're linearly independent, and therefore they're forming a basis for my eigenspace. But once I've established that, and these are a basis, I can generate as many eigenvectors as I want. What's the dimension of this eigenspace? 2, right? I have 2 elements in my basis, so the dimension of the eigenspace is 2. And then, since I can find infinitely many eigenvectors, all I need to do is find another 2 that are linearly independent, because any 2 vectors from this space that are linearly independent will also be a basis for the eigenspace. So what am I going to do? I'm going to start creating vectors. What if I did this? What if I found a new vector, x3, and it happened to be 1/2 x1 plus x2. I'm just going to add them, right? I can generate more eigenvectors by taking a linear combination of my basis vectors. That's what I'm doing. But when I do this thing, when I actually add these vectors, I'm going to rewrite these. This is going to be 1, 1 minus 1 or 0, 1. And this one's going to be 1, 1 plus, I'm sorry, I, I've got my I in here, plus I times 0, 1. I'm just writing that in real and imaginary part. But when I add these two things together, add this thing plus this thing, well, I'll get 1, 1 here, minus I times 0, 1, plus 1, 1, plus I times 0, 1. Those two things are going to cancel out. So when I add these two vectors together, I really get 1/2 times, well, I'll add these two together, 2, 2, I will get the vector 1, 1. Now, is x3 in my eigenspace? Sure, because it's just a linear combination of my basis vectors. It has to be in my eigenspace. So this is an element of my eigenspace. I'm going to do another one. I'm going to find another one. Let's take negative 1/2 I times x1 and I times x2. That's an odd combination, right? But I can do it. Right? Any multiple of my vectors are still in a space. Doesn't matter if that scalar is I. I'm allowed to do that. And when I do this one, let's see what I get. I get negative 1/2. I'm going to multiply my first vector by I. I'll have I times 1, 1 minus I times I. What happens when I take I times I? I squared is negative 1. So those negatives cancel out. And I get this thing. So that's my first. And I'm subtracting my second one. Well, I times my second vector will give me I times 1, 1. And then I times I again will give me minus 0, 1. Negative 1/2. Now I have this thing minus this thing. Those are going to cancel out. I have a negative and a positive, so I'm really adding those two vectors. And I'm getting 0, 2. Okay, so I don't want to multiply by negative out here, just positive 1/2. Tweak that sign. And the net result will be 0, 1. Is 0, 1 in my eigenspace? Is 0, 1 linearly independent with respect to 1, 1? So now I have two vectors from my eigenspace that are linearly independent, which means these two can be a basis for the eigenspace. They are a real basis. And so those are what I'm going to use for my new basis. Now, why did I take 1/2 in the sum and 1/2 in I times the difference? Is that what I needed to do? Am I going to have to do that every time? Or is there something special about 1, 1 and 0, 1? Back to my eigenvectors. What I've done here was I've taken linear combinations specifically to generate just the real part and just the imaginary part of my eigenvectors. All right, so I don't have to do this every time. The process is you get your eigenvector, and instead of putting the columns as this and this for P, use the columns as this vector and this vector. The real part and the imaginary part. That's all we're going to do. Now I go through that process to show you that why are we just randomly grabbing parts of the eigenvector? Because really, these are a basis in themselves for the eigenspace. So this is really just the real part. This is really just the imaginary part. And what I'm going to do, because those are also a basis, is I'm going to say P is now going to be a matrix that's formed from the real part of the eigenvector and the imaginary part of the eigenvector. I'm going to use those as my columns instead. So no, we don't have to do that work every time. Instead, we just go like this. You take A, you find your eigenvalues, you generate your eigenvectors, you write this as a real and imaginary part, and you grab those pieces and put them into the columns for P. And now that just leaves us with D. Normally we use the eigenvalues on the diagonals. But those eigenvalues are complex, and I want real values in this matrix. So I'm going to do a little thing to figure out what P has to be. I'm looking for this thing. I know what A is, now I know what P is, so instead I'm going to go like this. If I take this equation and multiply both sides by P inverse, I will get P inverse times A equals D times P inverse. If I right multiply both sides by P, I'll get P inverse A, P equals D. I'm just solving for D. And I can do that because I know the inverses exist in this case. So I'm going to see what P has to look like. I'm going to take the P matrix. I'm going to take this matrix and P inverse. Actually, P inverse is kind of easy to generate in this case. It's just this thing. I can go through the formula, but I know what this vector does as a row operation, so I can just reverse the row operation. Or you can just take my word that that's the inverse. All right, we're a little crunched for time, so I'm just going to do this calculation here. When I multiply these out, this is the vector I get, or the matrix I get. This is the matrix I get. It's not diagonal, which is a little frustrating. It'd be nice if I had a nice diagonal matrix. But remember that the reason I wanted that diagonal matrix is because I could definitely see what that matrix did as a transformation. I can actually see pretty easily what this matrix does as a transformation as well, because it has a special form. Anyone recall what this kind of matrix does? It's a little harder to see in the numbers. But really what we're looking at is the symmetry. I have the same values on these diagonals and these diagonals, and there's just a sign difference here. We worked with a matrix kind of like that before, except it had a bunch of sine and cosines in it. This is actually a rotation matrix for some specific value of theta. Remember that one looked like, I think it was cosine, sine, negative sine, cosine, something to that effect. It has those same symmetries. So this actually does a rotation. So the result is a little different for complex values. We don't actually have A equals P times D times P inverse. Instead, we have A is equal to P times C P inverse, where C is a rotation matrix. But once again, the value is still there. We still know what the transformation does through this decomposition. So let's formalize everything and give you the nice formula stuff here. Here is our formula. You have A, and when you have complex eigenvalues, note here I have a minus eigenvalue here. You find the associated eigenvector. Then our decomposition is going to look like this, with a C instead of a D, because this is not going to be a diagonal matrix. And what's P? P has the columns of the real and imaginary part, the eigenvector. And C uses the real and imaginary parts of the eigenvalues. So the real part is on the strong diagonal, the imaginary part is on the weak diagonal. And then you just be careful with the signs here. So we'll take a little carefulness here to make sure you have your B's and your minus signs right. So do a couple and make sure you have it down. All right. Any questions about that? Essentially, it's not that different from what we've done. Just a little bit different. A lot of the mechanics will be the same, but it's just a mechanical process. It's just something we have to go through again and again. All right, the last thing I want to show you is another way to kind of think about this stuff. You go to Wikipedia and search eigenvectors. It'll bring you up a big page. And there's a specific thing I wanted to show here. They have a nice graphic. This one right here. So he talks a lot about what these transformations do. So as we watch this little graphic spin over here, we'll put it bigger. What this is showing is a set of points being acted upon by a transformation, by a matrix. It's taking all these points and multiplying them by a matrix. And they have these little vectors inside of them. And what they're showing here is that for this matrix, they find the eigenvectors, and they're representing those vectors as the blue lines and the pink ones. And what you notice when this thing transforms and it stretches is that these don't change direction at all. All they're doing is changing length. It's just scaling those vectors. Well, that's what an eigenvector does. Right? Matrix times vector just scales the vector. It goes lambda times vector. So in this transformation, these don't change orientation at all. Whereas if we look at the red one, just some random vectors, you can tell as it stretches, it's pointing straight up, now it's pointing over to the right a little bit. They change their orientation based on the transformation. Now, when you think about what happens in the complex case, we have complex eigenvectors. They're harder to draw on this thing. And that kind of makes sense, because now we see that inside of a matrix transformation that involves complex eigenvalues, there's really a hidden rotation. And if there's a rotation, there's not going to be any real vector that doesn't change its orientation. That's why we get these complex values, because it's really a rotation in disguise. Another way to think about this. Another way to think about these eigenvectors is that these are the vectors that keep their orientation under the transformation. All right. All right, that is what I'm going to close with for today. We're getting close to test time. It's on Thursday in class like normal. We'll do the same thing as last time. I'll show up a little early if you want to get a jump on the exam. I will write it to be an hour exam, but I won't write it to be longer. Tomorrow, however, we are going to get into 6.1. We'll do kind of introduction to vocabulary, so read through that section. Hopefully we have a little bit of class time to go through any questions you might have, a review. I didn't post a practice exam. That quiz we took really was kind of a practice exam. I tried to make it big and kind of broad. So we'll go over that, go over your previous exams, lots of homework problems, and bring questions if you have them. And office hours are right now.
So they're called eigenvectors then? Because eigen means same, right?
Yep.
Eigenvectors say the
Same vector, yep.